In this video, we're going to run through the basics of the internal combustion engine. We're going to talk about the engine location, types of engines, the strokes, firing order, cam location. We're going to specifically look at valve overlap. We're going to talk about engine size, torque, horsepower. Then in the next video, we're going to take a look at the lubrication, oil, and the cooling system. Today's engines, first of all, must run clean. We have California Air Research Board, which has tighter emission standards than the Environmental Protection Agency. There are about 13 states that have adopted California's emission standards instead of going with the federal standard. Washington, Oregon being two of those. Next, they need to get good fuel economy. There is a corporate average fuel economy, which if you try to take a look at that, man, it gets really complicated with all the different ins and outs and all the stuff that they've done politicking with that. The engines also need to run smooth. If you've got an engine that hesitates, runs rough, people are not going to be happy with that. It's going to get that reputation and they're not going to be able to sell that vehicle. Then last, they need to have good performance. With the performance, if you go back to the muscle car era where we were looking at 300 plus horsepower and the V8s at that time and getting somewhere between 8 to 12 miles per gallon. In the mid 90s, the engines today started getting horsepower equal to the horsepower of the muscle car era. As we got into the early 70s and they had to start meeting all the emission standards, horsepower went away, performance went away. And we've got that performance back now, plus a lot more. We can get 30 miles per gallon, even with all that horsepower. Today's engines are smaller, lighter, more economical, and they last longer. Hats off to the engineers for that. Engine location, what you really want to get is a 50-50 weight distribution. However, to put the engine in the middle of the car where you get that, you're going to be limited on where you can put people at. Most of the vehicles that you're working on today are going to be front engine, and what that means is that the engine is over the top of the front axle or in front of the front axle. A mid-engine means that the engine is in between the two axles. A rear engine would be behind the rear axle. The Volkswagen Beetle, Chevy Corvair, those had air-cooled rear engine. The problem with the rear engine, you got all that weight in the back. If you get on a slippery condition, hit the brakes, that car goes around on you and the back end starts leading because that's where all the weight is. With Tesla's Roadster, they had the battery pack, the motor, controller, all that weight in the back of the vehicle. Tesla would not allow you to disable the traction control because they did not want that car spinning around. Engine types, you have inline over here. This is showing you an inline 8, which you're not going to see that anymore. This is your V engine, which this one happens to be a V4 cylinder. However, most of them that you're going to be seeing are V6 or V8 engines. The third design, the Volkswagen Beetle, Chevy Corvair, they had the horizontally opposed engine. Porsche also went with the horizontally opposed engine. Subaru is the manufacturer that you will find using this horizontally opposed engine or this boxer engine in their vehicles. I think just about everything coming from Subaru has this engine. The advantage, low center of gravity. And that's the reason that Subaru's king in the rally racing. The disadvantages, your crankcase is 2 pieces, and there's no extra charge for the oil leaks on the Subaru engine. The 4 strokes, in order. We have our intake stroke. Piston is going to be going TDC, or top dead center, to bottom dead center. Intake valve is open. As the piston goes down, it creates a cavity in here, which is a low pressure area or vacuum. The pressure in the intake manifold, which if the engine is at idle or at cruise, generally you're only going to have about 5 pounds of pressure inside of the intake manifold, as opposed to almost 15 pounds of pressure outside of the intake manifold. That is going to push the air and try to fill up the cylinder. Once we get to bottom dead center, we're going to start the piston back up, close the valves, and there's our compression stroke. Get up just before top dead center, we're going to fire the spark plug, and now the burning of the air-fuel mixture is going to push down on the piston. For our power stroke, before we get to bottom dead center, we're going to open up the exhaust valve. Piston's going to come back up through the exhaust stroke. Before we get to top dead center, they're going to open up the intake valve. And we're back over here on the intake stroke. Pistons starts going down. They're going to close the exhaust valve. And we start our 4 strokes: intake, compression, power, and exhaust. Suck, squeeze, bang, and blow. If that helps you and makes it easier to memorize the 4 strokes in order. One real critical stroke for engine performance is that intake stroke. That's where we're going to develop the low pressure area in the intake manifold. That is what the computer is going to be looking at to determine engine load. It is manifold pressure. With the 4-stroke engine, it's going to require 2 complete revolutions of the crankshaft to complete our firing event, which on a 4-cylinder engine, that means we're only going to have 2 firing events with each revolution of the crankshaft. Typical inline 4-cylinder, cylinders 1 and 4 are going to move up and down together. Cylinders 2 and 3 are going to move up and down together. Over here looking at the firing order, we have our first cylinder, which this is going to be our cylinder number 1. Power stroke, piston's going to be going from top dead center to bottom dead center. Then we have the exhaust stroke, piston's going from bottom dead center to top dead center, our intake, and then our compression stroke, and back to the power stroke. I'm going to skip down to the 3rd cylinder, so we'd be looking at this cylinder right here, and this is saying when 1 is on the power stroke, that means it's going from top dead center to bottom dead center. This is saying number 3 is on the intake stroke, which would also be top dead center to bottom dead center. But if 1 is going down, 3 is going up. This 1st, 2nd, 3rd, and 4th cylinder is not 1, 2, 3, and 4. On a typical inline 4-cylinder, firing order is 1, 3, 4, 2. Cylinder number 3 is the 2nd one in the firing order. When 1 is on power, coming down, 3 is on compression, going up, number 4 is on intake, number 1 is going down on power stroke, number 4 is going down on intake stroke. Now as you look at this and think of this in cylinder 1, 3, 4, and 2, which is your 1st, 2nd, 3rd, and 4th cylinder in the firing order. This is real important to understand, real critical. If you didn't catch this, either rewatch this section of the video, read it in the book, find something else so that you understand what the firing order is. Going through some of the more common engines, we've already talked about the inline 4-cylinder. This one is showing you the distributor in a clockwise rotation. Cylinder 1, 2, 3, and 4. So here's our number 1 in the firing order. Next is number 3, number 4, and then number 2. Typical inline 6-cylinder firing order is 1, 5, 3, 6, 2, and 4. This one also has the distributor in a clockwise rotation. You're going to have a spark plug wire coming to here. This next will be here, and there's your 1, 5, 3, 6, 2, 4. V6 engines, there's 2 typical firing orders for those. This is showing you 1, firing order 1, 2, 3, 4, 5, 6. Pretty straightforward. The other common one for a V6 is 1, 6, 5, 4, 3, 2. There are other V6 firing orders, but these are the 2 most common ones. Now we're going to take a look at the V8 engines. We're going to take a look at the Ford V8. Front of the engine is down here at the bottom. Cylinder number 1, right-hand side of the engine, and Ford numbers on 1, 2, 3, 4, 5, 6, 7, 8, as opposed to this V6, which had the odd number cylinders on the right, even number cylinders on the left. Ford does 1 through 4 and 5 through 8. Ford has 2 or 3 different firing orders that they've used on their V8s. This particular one is a 1, 5, 4, 2, 6, 3, 7, 8. You would find a spark plug wire coming across from there. Their distributed rotation is counterclockwise. There would be a plug wire coming to number 5 from here, number 4 from here, across like that. GM's firing order, 1, 8, 4, 3, 6, 5, 7, 2. GM puts their number one cylinder on the left side, and they do odd on the left, even on the right. What the manufacturer does is the head that sits forward is where your number one is going to be. Connecting rod for number one and connecting rod for number two on the GM, connecting rod for number one and number 5 on the Ford share the same journal. One has to sit forward of the other, which means the head on the engine on this side is going to sit forward of the other one. That's where they start their number one. When we get to OBD2 and we're talking about bank 1 and bank 2, bank 1 is always the side of the engine with cylinder number 1. So on the Ford, it's the right head. On the GM, it's the left head. The pushrod engine has been around for a long time. I actually came across a shirt when I was doing some research, and on the shirt it read, "Long live the pushrod engine." Well, I think its days are numbered. There's a lot of advantages to the overhead cam and dual overhead cam engine that the pushrod engine just can't keep up with. Primary advantage to the overhead cam is when you get to the variable valve timing. That's really difficult with a single camshaft sitting down in the center of the engine. Looking at this right here, here's our camshaft in the center of the engine. Push rods coming up to our rocker arms, and you got this display right here. So there's a lifter right here that's going to be pushed up as the lift on the camshaft lobe comes around. Pushes the lifter up, pushes the push rod up, pushes the backside of the rocker arm up. This side comes down, pushing down on the valve. What you have is a lot of reciprocating mass. That's the disadvantage to the pushrod engine, is all the reciprocating mass. If you think about the mass, the weight here, the amount of energy that's going to be used to get this moving, then you have to get it to come to a stop, and then you got to get it moving back the other direction. That's wasted energy. The other disadvantage when we get to the variable valve timing with a single camshaft, it gets harder to adjust when you want to adjust the intake and not the exhaust. Now that I've said that, if you do some research and take a look at Fiat's setup that they have, man, that's a nice little setup for the variable valve timing, which I've heard a rumor that Fiat is going to start selling that system to other manufacturers. You may end up seeing that. Advantage, smaller package. The heads on a pushrod engine are much smaller than the heads on a overhead cam or dual overhead cam. You can get the engine into a smaller area with the pushrod engine. The disadvantage, we talked about the reciprocating mass. Single overhead cam engine, we pulled the camshaft out of the block, put it up here on top of the head. Still have the rocker arm, but we eliminated those large lifters. We eliminated the push rod, so we got rid of some of that reciprocating mass, making this engine at least theoretically more efficient. The other advantage to a overhead cam is you can get a higher revving engine. The disadvantage to this, a lot of machining has to go inside of this head. They become more expensive. And then when you have a V engine, a single overhead cam actually has 2 camshafts. Get to the dual overhead cam, you can see we got rid of the rocker arm, so we got rid of more reciprocating mass. We still have this lifter, which is pushing on the valve. That's going to be your adjustment for the valves. We can also work our variable valve timing because we can phase the exhaust valve different from the intake valve. The disadvantage to the dual overhead cam, again, is expense. You have a lot of machining to get the camshafts in here. If you have a V engine, a dual overhead cam is actually going to have 4 camshafts. Larger head, more money, but again, the higher revving, at least theoretically, more efficient. In order to turn the camshaft, remember we're going to turn the camshaft at 1/2 crankshaft speed, so this gear is going to be twice the size of this gear. The disadvantage to this, man, that gear is pretty big. It has a lot of weight. The manufacturers later went to a fiber gear like this one here, which you have a lot less weight. It also had the advantage of being quieter, but if they did not change the oil often enough, this fiber gear would wear, then it would get really noisy, and then it would shear some of the teeth, and now you're taking a chance of bending valves as they hit with the pistons. Second way of doing it is using chains. On this dual overhead cam engine, you can see it's a dual roller chain. This one is off of a pushrod engine. Then on this dual overhead cam V engine, look at the length of this chain. And that thing is really long. It's going to be a lot of weight. The more weight that you have, you're going to lose some efficiency. Then this also has 3 chains, because besides this chain that is turning the intake camshaft, there's a second chain here and a third chain over here. So you get a lot of weight on this. The advantage of it, as long as the person keeps their oil changed, that chain is going to last the life of the engine. Third way of doing it is using a cog belt. Big advantage of the cog belt, they're quiet. They're less weight, so you have less mass to there. I think that's the reason that you see most of the engines that are out there are using a timing belt instead of a timing chain. The disadvantage of the timing belt, it is a maintenance item. Early ones needed to be replaced about 60,000 miles. They've now got them where they're going to get 90 to even 110,000 miles. If you buy a used vehicle, or if a customer brings a vehicle in and they bought it, and you're trying to find out, hey, was this belt replaced? Because they may have 100,000 miles, and the customer is going to say, I have no idea. What I do is I pull one of the covers off so I can look. You're going to look in this area right here. As you can see, this cog doesn't fit. Inside of there, there's a gap on that. As that wears, it's going to wear on the side of this cog. If I look inside there and there's any sort of a gap, even just a small gap, I'm going to tell the customer, no, it's time to replace this. If it's got 100,000 miles and that fits down inside there real well, and there's not the wear on the back side of this belt, it's been replaced, because it's not going to look new at 100,000 miles. Interference versus non-interference engines. What the interference engine is, if you have a valve that's all the way open, and the piston in that cylinder comes up top dead center, those two hit each other, and it's going to bend the valve. They're what they call non-interference engines, meaning, yes, the valve can be all the way open, piston can be top dead center, and they don't contact. I worked on my sister's little Honda Civic that she had way back in the early 80s, and she had a non-interference engine. Her timing belt broke, and it bent half the valves in the engine. The reason this non-interference engine bent the valves is because the carbon that builds up inside of the combustion chamber, there was carbon built up on the valve, there was carbon built up on the top of the piston, and that carbon hit and it bent the valves. So volume 1, this is the piston at top dead center, and you put a liquid in here to see how many cc's of liquid this would hold. Then you take the piston all the way down at bottom dead center, and how many cc's of fluid does this volume 2? Volume 1 plus volume 2 divided by volume 1, there's your compression ratio. In the emissions days, so the dark days for the engines in the early to mid 70s, we were running 7.5, 8, 8.5 to 1 compression ratios. The engines today are running much higher compression ratios because they figured out how to clean it up even with a higher compression ratio. We've got some of the newer engines like the Mazda. I think their newest engine is pushing almost 15 to 1 compression ratio. But what they're doing is they're keeping the intake valve open during the compression stroke. So they're running it like a low compression engine. And that's what they call an Atkinson engine. We'll get to that, or an Atkinson style engine. And we'll talk about that in a little bit. Volumetric efficiency. Let's say that you are operating your vehicle at sea level. Atmospheric pressure is 14.7 pounds per square inch. To get 100% volumetric efficiency, that means when this piston gets down here to bottom dead center, you would have 14.7 pounds per square inch in here. On a naturally aspirated engine, there's no way that's going to happen. Beginning of the intake stroke, the piston is going to be up here at the top. It is pulling down through the entire stroke. The intake valve is open. We're creating that low pressure area in here. The intake manifold, which if you're at idle or if you're in a cruise condition, you're only going to have about 5 pounds of pressure in the intake manifold. That 5 pounds of pressure is what is going to force the air or the air and fuel into here. At 1,000 RPM, the intake stroke, top dead center to bottom dead center, takes 30 milliseconds. Even at that low of an engine RPM, in 30 milliseconds, you're not going to be able to get enough air in here to get 100% volumetric efficiency. The only way you'd get 100% volumetric efficiency, or the only possible way to get it, is if you have a forced induction engine. Most of the time, we don't need to fill the cylinder. If the engine is idling, we just need enough power to keep the engine turning. Even at cruising, if you have a small car, you may only be drawing about 30 horsepower. The more air or fuel you can get in here, the more power you can get. So at wide open throttle, that's where we want to be able to fill it up. Next, we're going to be talking about valve timing and valve overlap. We're going to focus on this valve overlap and advantage, disadvantage to the valve overlap. We're going to be using the term scavenging. Now, we're going to be taking a look at 2 revolutions of the crankshaft here. Looking at this one first, here is our top dead center. We're going to be on the intake stroke. Before we begin the intake stroke, here's where the IVO, or the intake valve, opens at 20 degrees before top dead center. We're going to keep the intake valve open for 180 degrees during the entire intake stroke. Then for another 35 degrees of the compression stroke, the intake valve is still open. 20 plus the 180 plus the 35, 235 degrees of crankshaft rotation. First time I went to look for a camshaft to put in a car, and I'm looking at the specs, and it's saying, 230 or however many degrees. And I was thinking, wait, man, you've only got 360 degrees in one rotation, and that valve's open for 200? It's like, there's no way, this can't be. And it took me a while to find out that, they're measuring valve opening in crankshaft rotation. Remember, camshaft is half the speed, so cut that number in half, and you can see how long the camshaft holds the valve open. 35 degrees into the compression stroke, we're going to close the intake valve. Now we've got both valves closed through the compression stroke. Before top dead center, they're going to fire the spark plug. Both valves are closed through the power stroke. And then here on this one, 35 degrees before bottom dead center, they open the exhaust valve, open for 180 degrees, and then for another 10 degrees. Between here and here, that is where both the intake and exhaust valves are open for this 30 degrees of rotation on this particular engine. If both my intake and exhaust valves are open, the one thing that can happen is the air and fuel, assuming it has fuel mixed in with it, that air and fuel coming into the combustion chamber from the intake can go right out the exhaust, which means I'm going to have high hydrocarbon emissions going out the exhaust. At idle, at low RPM, I do not want very much valve overlap. When you get up in higher RPM, to have a lot of valve overlap is really good. It helps in called scavenging, so it helps push more of the exhaust out, so you can have a larger gulp of fresh air, fuel, get more power from it. If you've never been to the drag races, I would really encourage you to go at least one time. It's gotten really expensive to go, so I don't go much anymore. But when they take those AA funny cars, which are pushing somewhere between 8,000 and 10,000 horsepower, and they start that thing up, and that engine sits there and goes, it's just barely running. You're thinking, man, this is crazy the way that's running. What you have is the excessive valve overlap that's causing those misfires. Get up in higher RPM, man, that engine runs smooth. That's where you want the valve overlap. We have a Ford Ranger that somebody dropped a V8 into that, has aggressive camshaft in there. One of the instructors years ago, he wanted me to get that thing to pass emissions because he wanted to be able to drive it around to take it to other schools. I'm telling him, I go, man, there's no way. They said, but I'll try it. So put the gas analyzer on there, start it up, and I'm adjusting the carburetor, trying to get that thing leaned out, but not too lean. And as I'm adjusting that, 1,200 parts per million. That was the cleanest I can get it, which That's more than 5 times what it was allowed. Take it up to 2,500 RPM, it was clean. Even without a catalytic converter, that engine would pass the emission test at 2,500. So valve overlap, good at high RPM, high engine loads, bad at low RPM and light engine loads. Here's where you're going to get your Atkinson engine with a variable valve timing and the ability to phase the camshafts as they can adjust that valve overlap for RPM and for engine load. Let's take a look at one more engine here. This one here, they're going to open up the intake valve 21 degrees before top dead center. Through the intake stroke, it's open for another 180 degrees, and then on this one, 51 degrees into the compression stroke. Close the intake valve. Both valves are closed through the compression. Jump up here. There's our power stroke. Both valves closed through the power stroke. And then we get right here, 57 degrees before bottom dead center of the power stroke, we're going to open up the exhaust valve. The piston is going to get most of its push right in this area here. As the piston gets farther down, it's going to have less and less push, so it really doesn't hurt to open the exhaust valve, and it helps to get the exhaust out of there because we've got that high pressure and it starts it moving. 57 degrees before bottom dead center, we open the exhaust valve, keep it open through the 180 degrees, and then you see right here, 21 degrees before top dead center, open the intake. So from here, both exhaust valves are open, both the intake and exhaust valve are open, to right here, that's our valve overlap. Multiple valve. So for a long time, all the engines had just 2 valves. One, the larger one is going to be your exhaust valve, intake valve. The larger the valve, the more air you can get into the cylinder. But if you look at the size of this spot right here, you can't get any bigger valve inside there. But if you take 2 valves, you actually can get more air through the space of the 2 valves than you can with this one. The whole purpose for putting a multi-valve is improved volumetric efficiency. Sounds like a good test question to me. We're going to go through this fairly quick. If you're in my class, you're going to see this on the final exam. You have to be able to calculate the size of the engine. So you do want to understand this. The reason I'm going to go through it very quick is because 1, it's in the book. They'll show you how to do it. 2, there's a lot of websites you can just put in the bore, the stroke, and the number of cylinders, and they'll go through and do the math for you, so you don't have to do this yourself. What I will warn you about is there's a lot of websites out there that will give you this formula, but they give you the wrong formula. The wrong formula, where they miss it, is this spot right here. What they will tell you is pi times bore times the stroke times the number of cylinders. If you do that, you'll get the wrong size engine. You have to use the radius, half the bore, squared. It's a 6-cylinder engine. It has a 3.35 inch bore and a 3.46 inch stroke. Half of the bore is 1.675. We're going to take the 1.675 times 1.675 times 3.1416, which is pi, times the stroke, 3.46, times 6 equals 182 cubic inches. To convert your cubic inches to liters, divide this number by 61, which is going to give us 3-liter engine. 61 is a rounded off number. It's not exactly that, but it'll get you in the ballpark. You can do the same thing with metric. Here we have the exact same engine, 85 millimeter bore, 88 millimeter stroke. The millimeter needs to be converted to centimeter. This is where I had the hardest time, was trying to figure out, okay, how can I do this math? And it kept coming out wrong. 8.5 centimeters, 8.8 centimeters. That's your bore, 8.5. Half of the bore is a radius, so 4.25. You're going to take 4.25 times 4.25 times 3.1416, which is pi, times 8.8 centimeters, which is our stroke, times the number of cylinders, which is 6, gives us 2,996 cubic centimeters. To convert that to liters, decimal point is right here. I'm just going to move this over. It is a 2.996, which they always round off. And there we have it, our BMW 3-liter engine. There's your two math formulas, one for calculating using inches, the other for calculating using centimeters. Torque versus a horsepower. Torque is a measurement for twisting force, remembering that you can apply a twisting force and not have any movement. So if you're torquing something down, you're pushing, twisting on that bolt, even if it's not moving, you're still applying a twisting force. So torque is a force, whereas horsepower is a measurement for work that is being done. Instead of going through and giving you all these different formulas and how this is done, what I'm going to do is just bring it to the end. And that is, if you want to race, if you want high performance, you want horsepower. If you're going to tow something, like say you have a 12,000 pound trailer or a 14,000 pound trailer, you want torque to be able to get that moving. For a racing application, let's say that you're racing with an automatic transmission, not able to do as much work at low RPM as it can in high RPM when the pistons are moving faster. So you get a high stall torque converter. You're sitting there at the line, power braking it. Left foot planted on the brake, right foot is on the throttle. You're giving it gas. RPM's at 3,000 RPM, so you're getting up close to your peak torque curve as you come off the line, get the light green, and boom, you can take off. Want high RPM, get you lots of horsepower there. On a truck, they're not going to sit there and power brake. They want to get the torque. They want to get that low-end twisting force. Now, if you take a look at this engine on the right here, during my power stroke, piston is coming down. The connecting rod, this is where it's going to push, is at this point right here. And let's say that this is 2 inches out from the center line. If you're applying torque to something and you've got a ratchet that has a 1-foot handle, and you take that ratchet and you get a breaker bar that has a 2-foot handle, you can push the same amount farther out and get a lot more leverage. That's what we're going to do. On this one here, we've moved this out to 2.5 inches. Now, if the piston's coming down and the piston is giving the same amount of push, but I am a 1/2 inch farther out right here, I'm going to get more twisting force. On the diesel engines, they're going to have a long stroke to get lots of low-end torque. It's going to be a low revving engine because they're getting their torque at low RPM. On your performance engines, they want high RPM, so they're going to go with a short stroke. Now, what I did was I brought in 2 extremes for you. One here is your Formula One racer, averages about a 40 millimeter stroke. Your RPM on a Formula One is going to be somewhere 12,000 to 15,000 RPM. It'll vary as they go through the years and change the requirements for the engine. The GM Duramax diesel engine has a 99 millimeter stroke. You can see that stroke on the Duramax is twice as long. It's going to be a low revving, a lot of low end torque. Formula One, high revving, short stroke. Engines are not efficient. You take 1 gallon of gas. As you burn this gas, how much heat energy is created? As we do that, over 30% of the heat that's generated is going to go out the tailpipe as heat in the exhaust. Another approximately 30% is going to be heat out of the radiator. We lose about 70% of the heat just from the radiator and out the tailpipe. We're also going to have mechanical losses. Our reciprocating mass, converting that to rotary motion, which that's the job of the crankshaft. Also, our conversion. We're taking a chemical energy, we're turning it into a heat energy, which is then turning it into a mechanical energy. So we have losses as we change that energy. We also have friction losses in the engine. We have mechanical losses through the transmission and the rest of the drivetrain. We're only going to be using about 20%, and most of the numbers I've seen are less than 20% of the energy produced to move the vehicle. A external combustion engine, like a turbine engine that they're going to use in a jet, those are actually somewhere 40 to 60% efficient. that finishes up this video. Hope to help.